All right, so to start off for assignment one, we'll go through some commands to show how the systems were created. Now, the OSs have already been installed on both virtual machines, so we're not going to run the initial commands that we'll explain, but then we're going to boot up the systems and we'll run some C code on it. So first off, to create our PowerPC system, we're going to emulate a Mac 99 PowerPC system around the Power Mac G4 era, early 2000s. So to do that, we use QEMU-system-PPC. We're calling -L to choose the BIOS that we're using. So we're going to use a PowerPC BIOS. We're going to say we're going to boot from the D drive. Since we're initializing the system and no OS is installed yet, we're going to picture it as a CD-ROM for the virtual machine. We're going to pretend that there's a Lubuntu disk stored in the CD-ROM drive. Where the machine's a Mac 99, we're going to use gigabyte of RAM for the startup, and then here we're specifying the disk image that we're going to use. So we previously created a Lubuntu 14 disk image with the QEMU -img create command. We just formatted a QCOW2 disk image just so we can have that ready, and we did that for both systems. We made one called Lubuntu 14.QCOW2, gave it about 20 gigs, and the other one we did called it HDA.QCOW2, gave it about all with the other one's .QCOW, and we gave it about 8 gigs. So yeah, for the first system, that's the command we need to run, and then here's the command to actually boot it. So in the meantime, let's get it booting because it does take a few minutes to boot this system. We're just going to paste it in there, put it aside, it'll start executing, and then we'll see. So to actually run the system, so we already pre-installed the OS, we're choosing the same thing, the PC BIOS, and then we're saying to boot from the C drive because we already installed the OS, so technically it's that drive. And then we're sending some program environment variables. So for the boot device, we're saying that it's off this hard drive, and then we're choosing Yaboot. Yaboot is the bootloader that's installed when you install Ubuntu, and then you can use it on PowerPC devices and such. And then we're passing some other boot arguments to the variable to the boot arguments here. Another thing to represent the hard drive, and then the actual file name of the Yaboot config. This is for, like I said, the bootloader to load the operating system. It's a Mac 99 machine. We're giving it 2 gigabytes of RAM. I believe that's supported. I looked it up. That's what's supported for these devices. And then we're saying we're also passing it where the volume is, the disk image that we created. So as this is loading, the next one is going to be MIPS-based machine. So we're going to be using a Longsun 3A1000. So we're choosing that as the CPU here. It's a MIPS 64-bit CPU, so we're using the command QEMU-system-MIPS64EL. So yeah, we chose this CPU with the -CPU flag, -M the machine flag. We're choosing the Longsun 3 virtual machine since we don't have a QEMU an option to. There's no physical machine to emulate there. As you can see, we're still loading the Ubuntu 14 image right here. This is the bootloader passing it over to the OS. So for the drive, same thing. We're choosing the drive. We're selecting the file. It's that HDA.QCOW disk image that we made. We're telling you what format it is. It's formatted as QCOW2. And we're saying the hard drive controller is VirtIO. You could use IDE. Well, IDE is not supported on this, or you could use SCSI. We're going to just use VirtualIO because the read and write operations are faster because this is made for virtualization. Then we downloaded a kernel. Oh, by the way, we also downloaded this ISO off of a FTP server that stores all these ISOs and stuff. Same with this one here. This is from a Debian FTP server. We're doing a Longsun 3 version of Debian 12.7. So we had to download this kernel image, and we had to download this like initial RAM disk image right here. So this is to initialize the RAM disk. So both of these were downloaded off the FTP server. We put them in the folder we're running QEMU in, and then we're passing these as arguments so the command knows where they are. The other thing we're pending is we're pending the root partition. We're using VDA here because that's what's required for the virtual I/O device. If it was SCSI, it would be SDA. Log level 8, these are just some commands to know that we are passing the console output and a lot of logs to the terminal output right here, because when you try running it otherwise, it doesn't run in the QEMU's GTK little visual thing. No graphic because we're doing it from the console, and then we're piping all the the bootloader and the kernel's output right to here to the console. So let's actually run it. When it comes to running it, most of the things the same. We don't include no KSLR. And then what we did, there was another step. We did have to mount this image. So after the operating system was installed, we don't have a bootloader for this MIPS device. So we had to use some commands to go into the virtual disk image that we created, the HDA.QCOW. We had to mount that. We went inside it. We copied this that was created by the Debian's installation process. This ramdisk.image with the long 610 long sun 3. This was created as Debian installed. So we mounted the disk image that we created, the virtual disk image that we created. We went inside of it, we copied this file out, and then we unmounted that disk image. So we're specifying the same kernel here as before because we need a kernel to boot. And then same thing, we're appending the drive so we know which drive it is, and we're piping the output to the serial monitor. All right, so let's get this machine booting at the same time. You can see here it does bring up this window, but there is no output in this window. This is just helpful though, because when I use -no graphic to run this, this X key kills the emulator, it kills the running program. And when this X isn't here, you can't use Control-C to send signals to kill it. So let's start logging into both systems. As you can see, we have a GUI here for Ubuntu 14. And then let's see the C programs that we have created. We'll compile them, we'll run them. As you can see here, the bootloader passed off to the operating system. Now the OS Debian 14's booting, setting everything it needs to do. As you see, like I said, there is no display in this image. I tried piping a display to this, but I'm not too sure if they have fully emulated display adapters for Long Sun 3. So this was easier way. All right, let's log into the MIPS-based system. All right, as you can see here, we are into the command line for Debian, and we are also into the desktop for Ubuntu. Let's get a terminal going on Ubuntu. This machine's a little slow. Let's focus on the MIPS first. There we are. CD into this directory. We have our file. Let's remove the old test run. So the little C file we have here, we were just creating a buffer file, using the file struct, creating a file pointer, some print text. So what we're doing is we're calling the lscpu command. We're just opening up a pipe and we're just syscalling the lscpu command and then printing the output in the C program, just so we can verify what architecture that this C program got compiled and is ran on. And before we do that too, let's clear the screen. Since this is emulated as a terminal, you can see that it doesn't clear like you would expect it to when you exit Nano and all that such. But first, let's just run lscpu by itself and shell. And you can see here we have all our processor information. We can confirm it is emulating a MIPS64 system. Processor's a Long Sun 3. This particular version, I believe, came out early 2010s, something like that. Anyways, so let's clear that, and then let's gcc main.c-o, let's call it main. All right, no compilation errors. We run it. We can see the text that we added, and then we get the same output as lscpu. Now let's do the same thing. You can see the cursors are a little disjoint here, if you can see that. But let's see where we are. Documents. All right, let's remove our old test. First off, let's do lscpu and confirm. Oh, sorry, no space. We can confirm we're running a PowerPC architecture. The models were actually, sorry, not emulating a PowerMac G4, we're emulating a PowerMac G3. Level 1, Level 2 cache. As you can see here, PowerPC uses a big endian byte order, and MIPS 64-bit uses a little endian byte order. But these C programs will be identical, and they will both compile on each machine. So let's clear that. Then let's nano our main.c so we can check it out. As we can see, it's the same thing. Same text, same syscall to lscpu, importing the same libraries, stdio, stdlib. All right, so if we gcc main.c-o main, see it compiled, /main, same thing. Our lscpu output still matches, our text is displayed, and it is all good to go.